Hi, my name is Todd Austin. I'm from the University of Michigan. This is a presentation I recently gave at a hardware security workshop, and the title is Hardware Security for the Win. The subtext of this talk is that software is pretty dangerous. So if you want to get good outcomes in hardware in security and privacy, you probably should start investing in your hardware security. Let's get started. This talk is arranged in 3 parts. In the first part, I want to talk about what's wrong with security today and how we can advance it from good to really great. In the second part, I'm going to shift gears and talk about what would privacy-oriented programming look like if we could reorient our current security to be really strong, cryptographic strength. It would provide a lot of capabilities for controlling what people could do with your data, essentially providing strong privacy controls. And then the third part, I want to talk about my work, which is TrustForge, which is a cryptographically secure enclave that can deliver that vision in part 2 using the approaches that we talk about in part 1. So let's get started. Let's talk about how we take security today from a state of good security to really, really great cryptographic strength security. So first, let's take a look at why security is not very secure today. And there's really 2 primary problems. The first is endless vulnerabilities in systems, in both software and hardware. These are typically design bugs that lead to attackers being able to step around the security mechanisms that are in place. And if we can find and fix all those bugs, we can really securitize the system. The challenge is, though, that the mechanisms that we have for finding and fixing bugs, like code inspection and formal software verification, formal hardware verification, they don't really scale to the level that you need to find and fix all the bugs. So you end up getting these, increasing number of vulnerabilities out there that are pretty much plaguing the industry. The second problem that we have is that even if you design a system that's completely correct in every way and doesn't have any vulnerabilities, it still may be leaking sensitive information through what are called side channels. Side channels are observable public properties that give clues to how secret information is being processed in the program. The example I always like to use is if you've ever watched a bank heist movie like Ocean's 11, when they go to crack the safe, they typically will take a stethoscope and put it on the safe. When they do that, you're using an audio side channel by listening to how the tumblers are moving inside of the safe lock mechanism. That side channel tells the safe cracker which numbers to use to try to open the safe. In a computing system, that leakage is through things like control flow of the program, how it accesses memory, the timing of requests and operations, how it contends with other programs in the cache, how its speculative execution code contends with other things happening. And eliminating these side channels is really challenging because there's this fundamental tension between performance-centric design, where we want to share resources and we want to optimize the common case, and side channel free design, where we don't want to do those things. So that tension usually ends up with performance winning and side channels being born. Just to kind of underscore the case for how bad security is today. There was a few years ago, NPR had an article where they essentially said about 70% of Americans have had their Social Security number stolen in the last decade. In fact, nearly half of them were in one breach around 2018 in the Equifax breach. So we're not very good at securing information today. I would say the reason we're not really good at it is because the approach we use to deal with security problems isn't a very durable path to security. And that approach is patching. Essentially what we do is when we see a system get attacked, we figure out what is the vulnerability the attackers are using, and then we patch the system. Now the problem with this is a bunch of problems. One is we're using attackers to essentially debug the security of our system. That is how we operate in today's world. In addition, we never find all the vulnerabilities because the attackers never find all the vulnerabilities. And in order to find all the vulnerabilities, we'd have to go through many of these attacks, okay, of course. But we're adding new code and functionality to our system all the time. And so this patching essentially continues forever. This also creates an asymmetric battlefield where it's easy to attack and it's hard to protect. Attackers only have to have one vulnerability. Sorry, I got a bird in my window. Attackers only have to have one vulnerability that they can leverage, whereas defenders have to have, they have to be able to fix all the possible vulnerabilities. Now, fixing all the possible vulnerabilities in the system really isn't possible today. Essentially, we create this scenario where in order for a system to be secure, you need to be perfect at finding and fixing vulnerabilities. And if you've ever tried to be perfect, perfection is essentially the enemy of progress. You can never get there. On the other hand, you only need one vulnerability to attack. In fact, it's so easy to be an attacker compared to a defender that in the attacker community, they have a pejorative term which they call people that don't know much about attacking. They call them script kiddies because they don't know anything about attacking, but they still know how to run scripts and make those attacks. So you end up with these systems that lack any protection for the vulnerabilities that haven't been discovered, and they also have no protections for new vulnerabilities that could potentially be discovered after they're deployed, what we call zero-day attacks. So how are we doing? Well, I always like to show the example of buffer overflows. The buffer overflow is a very simple attack, initially discovered and described in 1972 in this report. And this is from Microsoft Windows patch update, which occurred in mid-April of 2025, where they're fixing buffer overflows. So we're not doing a very good job at breaching secure systems through patching. So we need really a better way. To really understand why this patch-based approach is so difficult, I really want to just spend a few moments beating up on software. Software, which I like to call the root of distrust. Really, all the problems in security can pretty much be mapped to software. Before I talk about why software is so hard to trust, let's just define what I mean by trust. By trust, I'm talking about knowing for any part of the system precisely and for certain exactly what that thing can and cannot do. And if I want to trust it, I'm then going to decide if the set of can-do actions is a threat. If anything that the system can do is a threat, then I don't want to trust that component to maintain my security. Otherwise, I'll end up with a bad outcome. So let's look at what software can do. In particular, we're going to look at what's called attested software. This is software that's undergone an attestation process where software is developed, it's presented to a third party that evaluates it and says, yeah, this software is safe. And then we create a binary and we digitally sign that binary. This is things like, trusted execution environments like Intel SGX can do this kind of attestation. So if the software is attested, what can it do? It can do what the attestation indicates that it can do, unless the software gets hacked. So if the software gets hacked, then the attested software can essentially do anything, because hacking steps outside of the boundaries of what normal software can do through some vulnerability in the software. Now notice the attestation does not say there's no vulnerabilities in the software. It just says what the software wants to do is safe. If it gets hacked, it can then do anything. Now we can no longer trust that software. So what the community does is they verify the software formally, and they use safe languages like Rust, Go, or Python. Because safe languages prevent many kinds of vulnerabilities that attackers like to leverage, like the buffer overflow that we saw earlier. The problem there really comes when you look at hardware vulnerabilities like Spectre. Spectre is a hardware vulnerability that allows an attacker to misspeculate code in the microarchitecture and control what that misspeculated code is, and essentially leak information out of the system by having that misspeculation code manipulate the state of the microarchitecture. Because Spectre creates new functionality in misspeculation that attackers can manipulate that is not seen by the software verification mechanism or the safe language compiler, you essentially undermine all of the safety that the software verification and safe languages can deliver. Just as an example of this, if you follow my LinkedIn, you'll know in the past couple of years I've spent a bit of time on my LinkedIn doing Spectre attacks in Safe Rust. Safe Rust is a form of Rust code where you're not supposed to be able to access outside of the spatial and temporal bounds of an array in a Safe Rust program. But using the Spectre attack, I've shown that you can arbitrarily read past the end of arrays in Safe Rust. Why? Because the compiler, the Rust compiler, cannot see the underlying transient speculation code that I'm injecting into the machine. And so it cannot stop those attacks. And what I've found in general is that the software itself really is the problem with trust, not bugs in software, which traditionally people say if you fix all the bugs, then you can trust the software. It's really software itself that is the root of distrust. And for me personally, I've found that the quality of my security outcomes in hardware security have risen and become more strong and durable as I spend less and less of my energies trusting the underlying software. So really today, I'm really focused on what I like to call zero software trust systems. Systems which allow any software in the system to be hacked and it won't undermine the confidentiality or integrity guarantees that the system wants to provide. So how do we take the good security we have today and really sort of advance it to a much stronger state, a state that will actually allow these systems to provide not only better security, but also provide capability in the world of privacy? And we'll see why you need such good security to provide that. Well, the first thing we're going to do is we're not going to have the whole system be secure. That is a losing game because the complexity of the entire system is such that you'll always have vulnerabilities in your system. So what we want to do is we want to concentrate trust to a very small entity. And just like trusted execution environments, TEEs in the world today, we want to embrace this idea of the secure enclave, something that is small, something that is separate. Now, that's always not true for TEs today, but I want my security component to be completely separate from the main microarchitecture so I can have strong guarantees over what it can do, what it can leak. So we're going to build this trusted secure enclave. And we're going to eliminate all the software vulnerabilities. Oh, how do we eliminate all the stuff? You just told me that software is always hackable. So if software is always hackable, and we need to eliminate all software vulnerabilities, the only solution is that in the trusted enclave, there can be no software. Now, traditional TEEs have tons of software inside of them, and people hack the software. That is a sport in the world of trusted execution environments. Hack the software in the TEE. Now, the interface to TEEs are function calls, right? People call functions for the attested software that's in the TEE. If there's no software inside the TEE, the enclave, then what the interface is, we need a different interface. And the interface is just instructions. Add these two numbers together and give me a result. Divide these two numbers, give me a result. It's in the world of computer architecture, our lowest level of description of how we provide useful function is just an instruction set. So without software in the enclave, it's just got an instruction interface to the enclave. And then we're going to silence the digital side channels. Now, what's a digital side channel? A digital side channel is anything that's related to timing or contention. This is control flow side channels, memory side channels, timing, and microarchitecture. The alternative to the digital side channel is the analog side channel. And I definitely want to get rid of analog side channels too, but ultimately we're hardware. So that's another difficult problem. So what I'm doing at this point, I'm just separating digital and analog side channels. And I'm saying today I'm going to eliminate the digital side channels. Tomorrow I'm going to eliminate the analog side channels. So I'm separating that problem out. So today, all the solutions I'm talking about here today do have analog side channels. In fact, eventually I'm going to compare this technology to fully homomorphic encryption. And when I do that, the differentiating capability there is I have analog side channels, fully homomorphic encryption does not. I run 100 million times faster, fully homomorphic encryption does not. So there's a little bit of a trade-off there. I will attack those analog side channels sometime in the future. But right now I really want to separate out those two things because they're really separate concerns and endeavors. Right now we're just going to get rid of those digital side channels. And the way we're going to do that is through formal verification. We're going to separate that enclave from the main microarchitecture, no sharing with that. And then we're going to have mathematical proofs to say, oh, this does not leak through timing or contention, which is absolutely possible. And then finally, we need to protect information that flows out of this enclave because ultimately this information, it's in the database, it's in the swap space, it's all over the memory system and the caches and the registers. It just flows everywhere. It's our program. And anything that we want to protect, we need to protect it when it's outside. And the way you protect things in today's world, when they're not being computed upon, is you use best known ciphers on them. So we're going to encrypt that data. We're going to encrypt it with authenticated high entropy ciphers. Authenticated means that we can look at the ciphertext and tell you, yes, this is a piece of information that was created by the enclave. And high entropy means that it's pure random. So if I have 1,000 values of 1 encrypted in my memory system, they all have different ciphertext. So you can't essentially it prevents any analysis of ciphertext. And so we end up with this thing called the TrustForge Enclave. This is the work that I'm presenting at the end of the talk, which is this hardware-only enclave which lacks software or digital side channels, and it computes directly on encrypted data. And we'll see more of that in a bit. But first I want to kind of just shift gears and say, let's assume that thing exists. What does it mean in the world of privacy? And what does it mean for privacy-oriented programming? So let's take a quick look at that. Now, first I got to really describe to you, what do I mean by privacy? And it's interesting, I didn't, until a few years ago, I didn't really know the difference between security and privacy. I was just put security/privacy. Those are two, privacy and security. They must be essentially the same thing in my head. I bucketed them in the same. They're actually totally different. So security is the endeavor of stopping hacking. It is maintaining confidentiality on data. Nobody can hack in and see this. Maintaining integrity. Nobody can manipulate my instructions or my data. Nobody can replay information. And then availability. When I want to use this system, it has to be available to me. And we call this, in the world of security, we call this the CIA of security. Okay, that is security. That is the endeavor of security professionals. Privacy, on the other hand, is the endeavor of deciding who controls what can be done and what can be seen when it comes to sensitive data. A privacy-oriented system will give those controls over what can be done to that data and what can be seen about that data, typically back to the data owners, whoever owns the data. So like if I had a privacy-oriented social media site, I could put information into that site, but I could say only my friends can see that data. Not even the operators of the system can see that data. Not even the person that wants to do advertising recommendation can see my data, which of course creates these sort of difficult challenges where, they want to do advertising recommendation or that. These are really partially overlapping relationships. And I want to just pose a couple questions to show you the relationship between them. First, consider, can you have strong privacy if you don't have strong security? And the answer is pretty obviously no. If you don't have strong security, you could define privacy any way you want, and people will just punch through your security and steal your information and manipulate it in ways that you can't tell. So a precursor to strong privacy controls is exceptional security, going from good to great on your security. And without that, you can aspire to be a privacy oriented organization, but ultimately the hackers will change that for you. The second question I want to pose is, let's say we have strong security, does that mean we also then have strong privacy? And unfortunately, the answer to that question is no. There's no implication between strong security and strong privacy. Once you have strong security, you can have strong privacy controls, but that's an organizational decision. How many times have you looked at the New York Times and right under the first page fold is an article about another social media company which has excellent privacy practices, and internally they abuse our data in ways that are just eye-popping. So yeah, it's organizational to decide how to do that. The goal of privacy technologies is to really take the decision out of the organization and put it into the technology. So if I know I'm using this technology, I'm getting strong privacy controls. Why? Because I know that our organization can't see my data. By the way, one of the challenges as a hardware security person is trying to get people to use your technology. I've got a whole nother talk on this, but just to summarize the challenge, hardware security is something you have to add to every system you manufacture to improve its security. But when you sell a system, you don't sell its security, typically, in a consumer-grade system. Even in a data center, you don't really sell its security. It's expected to be secure. And so if you're adding a cost to the system for it to be secure, you are essentially putting a tax on that system. Privacy is different. By putting capabilities into a system where now you can allow someone to build a social media platform where we can provide cryptographic guarantees that the operators of the system cannot see your sensitive data, that's actually a value added capability. And often, and it's been studied widely in economics and the privacy world, customers will pay additional money to receive those capabilities. Companies can acquire more customers when they have those capabilities. So it's a bonus that your privacy capabilities can actually add a capability to your system. All right, so what does all this mean in terms of programming? I want to present to you the TrustForge programming model so you can see what does it mean to have a privacy-oriented programming capability. So the way we provide privacy in the system is everybody computes on encrypted data. That's why TrustForge, which is a microarchitecture technique, is often compared to homomorphic encryption, which is an advanced cryptography technique that also computes on encrypted data. But they're not the same. They're two different things altogether. But they have the similar goal that they don't want anybody to see any of this data unless it's allowed. So this is the privacy programming model of TrustForge. This person here, she's the data owner. So she's in control of what can be done and seen with her data. And she encrypts all of her data locally. And she delivers that encrypted data with a data contract. The data contract contains a PKI encrypted data key. We'll see that in a little moment. But PKI is essentially how you move keys around in the world in a secure manner. It's part of the public key encryption capabilities that exist. And she can also give a data grant for a specific part of the program, a function evaluation, where it will allow the user of that encrypted data to see decrypted the value of just that function g of x. And then the user of the data, that's actually the TrustForge Enclave user in the Ajeta Labs startup. That these are our clients. Our clients are the users of this encrypted data. And then this person is able to essentially compute any function they want, but the results of the computation are always encrypted. They can't know what it is the results they're encrypting, even though they're specifying the algorithm. It's all just random data to them. but they can actually send back any computation back to her, and then she can decrypt that computation under the original key that it was under, and she can also verify the result of that computation. And this is because TrustForge, unlike FHE and ZKP and all the other advanced cryptography technologies, TrustForge is proof-carrying computation. So inside the computation is a very concise proof of how that value was computed from her source data that she shared with the request, the initial request. And so she can verify, did you compute this value? Did you run an algorithm on my genetic data that I expected you to run it, or did you modify it in some way that I don't know about? That is a cryptographic proof that he presents to her, and she can go, oh yeah, you ran the algorithm I expect. That's awesome. But with the data grant, she can also allow him to run that g of x function and see the result of g of x, actually decrypt it locally in a way where he cannot decrypt anything else. It's a cryptographic strength mechanism, and for him to produce another function besides g of x and see the result of that with that data grant key for g of x, that requires what's called a pre-image attack on a cryptographic hash, and that is harder than Bitcoin mining. So it's a very safe mechanism. We call this, when the TrustForge Enclave user can see the result of g of x, we call that a safe disclosure, because he can only see the results of that specific computation. And the mechanisms underlying in TrustForge are guaranteeing that he did the computation on her data that she sent in this invocation, and that he computed specifically g of x as she knows g of x to be, and he see the result of that function. Pretty powerful capability. Now let's just see an example. How would you take those simple mechanisms? Those are the mechanisms that satisfy all of the privacy-oriented programming that we talk about in our research. And let's see how you can build an interesting privacy-enhanced surveillance mechanism. And what we're going to do, we're going to take something like a Nest camera. If you ever had like a Google Nest camera in your backyard, it streams data, video data from your backyard up to Google servers. Now it's encrypted over the link, but it's decrypted in Google servers. Then Google sends it into their machine language analysis framework to and it finds motion, faces, recognized faces, unrecognized faces, animals, pets. It's really cool. The ML layer can essentially tell you what's happening in your backyard, and then it sends that data back to your browser, and then you get a timeline. You say, oh, when was someone in my backyard? Oh, click right there, and you can, it highlights the timeline with these various events. It's a really cool capability. But, if somebody who's, a dishonest operator or a rogue programmer or a hacker comes into the system, they can see what's happening in your backyard anytime. That is, all the keys are available there. And so, fortunately, hopefully, that's the key, hope. Google has good security and privacy practices, and that's not happening. But there's no guarantee that cannot happen at all, because all the keys and all the data you need to abuse that information in any way is on those servers. And hey, if a judge come by and says, I want to see this information from this day, they may compel that organization to present that information. So in a privacy-oriented framework, we really want to send encrypted data up to the server. We want the server to perform computation on that encrypted data, do machine learning analysis that produces encrypted results that then are validated using the proof carrying code. And those validated results are then displayed on the timeline back in my browser, decrypted by me because I hold the key that encrypted the original data. That's beautiful. Now, if a judge comes by or a hacker comes by and says, show me what's in that server, then the organization says, I don't know what's in that server. It's just encrypted data. Here's the ciphertext. Go talk to that homeowner. They can tell you how to decrypt it. So it really sends the permission on who can do what back to the original data owner. And by the way, let's say I go on vacation and I want to tell Google, if you see someone in my backyard you don't recognize, send me a text message. Well, now I can create a data grant, give that to Google, and they can just see the result of intruder for my data that's being analyzed. They can't see the images, just that one Boolean value for the duration while I allow them to have that data grant. And so then if they see there's an intruder in my backyard, they can send me a text message to say, hey, I don't know what's going on in your backyard, but I did see that our machine learning framework said there's an intruder. Great capability. And you can just, if you go to my YouTube page, I've got loads and loads of applications that just use these very simple mechanisms. Oh, by the way, if someone hacks in and changes what they compute on the data, tries to do advertising recommendation, whatever, then they just see encrypted results. It's all corrupted. They can't find any results that are usable because they don't have the data grants for it. And when it comes back to me, I'm going to see that they did some alternate computation on it, and that's not going to work for me. All right, so pretty handy mechanism. If you had this capability, if the performance was where you wanted it, it would certainly be an amazing way to add value to a system where, clients of services could know with strong assurances that what was being done with their data. So let's take a look at how we implement this in my work, which is a device called the TrustForge Enclave. And the TrustForge Enclave, it's really inspired by Intel SGX and AMD SEV trusted execution environments, TEEs, but it boots out the software. It makes those components their own piece of hardware so that you can push them into becoming cryptographically secure. They don't worry about software hacking. They don't worry about side channels on control, memory, and microarchitecture contention. Let's see how we do that. It's pretty simple. It's basically just a privatized functional unit. They say the key to privacy is you have to protect data at rest, data in motion, and data when it's computed. But when we build systems to protect data when it's computed, there's loads of storage and other stuff that we stick into that box. We put whole CPUs and systems in that box. It's so complicated. So what you really want in that box is just the compute. And when you look at a CPU, just the compute is the ALU, the arithmetic logic unit. It's just that little tiny piece of hardware. And so what we do is we send ciphertext into that box. There we can decrypt it. We can verify that the way the box was built, that box is isolated from the rest of the microarchitecture, so there's no contention. And it produces this sort of provable computation through this proof-carrying mechanism. In the entire rest of the system, we have this encrypted, authenticated, and randomized ciphertext, which is really the best known form of ciphertext that's protecting our data everywhere else. If someone tries to manipulate it, we'll know it. If someone tries to send us something that isn't ciphertext that was produced by this box, we'll know it. It's a really powerful mechanism. And essentially, by doing this very simple change to the system, it is very simple what we're doing. We are denying programmers the ability to see the data that they're processing. This provides cryptographic strength security with respect to the software, and it provides a data privacy capability because now the system can compute on data, and the system and the operators and the programmers and everybody involved with that system cannot see the data that they're computing on. And that is really the essence of advancing data privacy. And people always go, oh, so you're doing homomorphic encryption and acceleration, which is fine. I love homomorphic encryption. It was a huge inspiration for this work, and I truly admire the work that's being done there. But this is not homomorphic encryption. The way I like to describe it is like when you want to build more advanced security, you need to get software out of the trust zone. And the only two ways to do that is through advanced cryptography, like homomorphisms in homomorphic encryption, or with trusted hardware that doesn't contain any software. And that's what we're looking at here. That's TrustForge. Now, the differences between these is advanced cryptography techniques are very expensive. The data is a million times bigger. The computation is 100 million times slower. Very, very expensive. To get better numbers than that, you have to build systems like levelized HE that are incredibly difficult to program, okay? But HE is amazing. It's amazing. If you look at the hardware, trusted hardware solutions, easy to program, floating point, strings, whatever you want. Minimal impact on your software. Minimal impact. We'll see this. But you got to protect those analog side channels. You got to protect leakage out of that hardware. If someone's going to be wheeling an electron microscope up to the box, if that's a threat, then you got to go to homomorphic encryption. So these two things really, they live side by side. Think of, hardware, trusted hardware is more of a consumer-oriented approach to encrypted computation. And homomorphic encryption, think of that as, the military grade, super expensive version of it. All right. So let's take a look. How does encrypted computation work in the TrustForge Enclave? Super simple. We've got that box. We've got that ALU, that trusted ALU that's off to the side, that is not leaking any information through timing or contention. And it's doing operations on encrypted data. It's decrypting, computing, and re-encrypting data inside the box. Which begs the question, how does it get access to a key? This problem was solved in 1976 by Whitfield Diffie when he invented public key encryption. So that's what we do. We assign to the functional unit a public-private key pair. Then the data owner sends a key that's encrypted under the private key of that ALU, encrypted under the public key of the ALU. And then when that's injected into the ALU box, the secret key, which is buried in that hardware, can decrypt that key. The CPU can't decrypt that key because it doesn't know what the secret key is in the ALU. The software can't because it doesn't know what the secret key in the ALU. Unless you're wheeling out an electron microscope to pull that information out of the circuits, you cannot know what that key is. So that key gets injected into the box using a very standard protocol. We use TLS 1.3, which is the same protocol that's used by the web. Once you have that key in the box, then you can do decrypt on the inputs, do the computation, encrypt, and send it out. And all you got to worry about is the latency of that encryption and decryption. You can do it for floating point, you can do it for strings, you can do it for integer, any integer size. It's really straightforward. What you end up getting in and out is these decrypted packets, these packets that are encrypted using a symmetric key cipher like AES. In our work, we use a symmetric key cipher that's very hardware friendly called Simon. And inside this packet is the data value that's being protected, a bunch of random data called salt, which essentially makes the output of the ciphertext pure random despite you encrypting the same values over again. So you can't analyze that ciphertext. A proof of how this computation was generated, we call that the data flow signature. And then also information about any exceptions that occurred during the computation, because the exceptions are not declared to software, because then you could say, oh, is this a zero value? Let's divide it into this value and see if we get an exception. The exceptions are buried into that encrypted packet, so there's a little bit of metadata there. And then when the data owner decrypts it, they can say, hey, there was an exception here. And then, then people always say, well, how do I get rid of the exceptions in my code? Well, you have to ask your data owner for a key to their original data if you're going to debug it. There's no debugging this information unless they provide you that access. So you really want to be sure that you don't have exceptions in your code. Outside of that box, the data is protected with this strongly encrypted, authenticated, randomized ciphers. So if it's manipulated in any way or forged, the system will immediately detect that. That's super powerful capability. Really eliminates trust in software and hardware outside of that box. And as a result, if someone hacks the hardware, they steal ciphertext. If someone does a Spectre attack, they steal ciphertext. If someone does a row hammer, you get an exception when you try to operate on those flipped bits. It's really, really powerful security. They need to attack that box. And by the way, I'll tell you, spoiler alert, that box is 190,000 gates. Super tiny. Super simple, super tiny. Now, unlike advanced cryptography techniques like fully homomorphic encryption, they don't check the integrity of your computation. But TrustForge does check the integrity of your computation. And it does this through what's called a data flow signature. A data flow signature ensures that the inputs to the computation were from this invocation of the function that is being run, and they came from the data owner. It ensures that all of the operands that are run are in the right order, and that the communication between the operands were of a data flow graph that was suspected by the data owner. And this is implemented as a one-way Merkle hash. A Merkle hash is essentially we send labels into the system right here, and then we hash the labels in the order they came along with the opcode, and then we send the result of that hash to the next op, and then we do this, what's called a Merkle hash, throughout the entire tree. Now the data isn't part of the hashing mechanism, just the structure of the data flow graph. So at the end, we get this output, which is the result of the structure of the data flow graph and the type of inputs that we had at the beginning. Now, as a result, we get this hash that's sort of well known for this computation, and when that hash comes back to the data owner, they can say, "Oh yeah, you did the computation I expected." So it's a really powerful mechanism. All this stuff is kept inside the encrypted packet. So if you try to manipulate the data flow signature, you blow up the data value. If you try to manipulate the data value, you blow up the data flow signature. So being in that single packet really provides a lot of strength from any type of manipulation. And so now if anybody does anything like swap an input or use an old input or add or delete an instruction or reorder any of the operands at a particular opcode, manipulate anything that's in memory or registers, or manipulate anything, in any of the instructions anyway, it's immediately detected. And getting around these defenses requires what's called a pre-image attack on a cryptographic hash, which is way harder than Bitcoin mining. So it's essentially impossible to defeat this mechanism. And I'll just say, if you're familiar with the Merkle hashes in Intel SGX, all they protect from this list is just this manipulation of memory. So just that one part of this list. This is a much more holistic approach to verifying computation, where this hash that's produced, we call it a proof, a concise proof of how the value was computed. Now, once you have that concise proof of how the value was computed, it's now possible to disclose values that are computed in an acceptable manner. That if that computation produces a privacy-preserving value, then the data owner can agree to provide you that information. Let me give you a quick example of how you might do this. Let's say we were building a machine learning training framework over encrypted data. And so if you looked at machine learning training, what you want to do is you want to take the data set, you want to run an epoch of training with backpropagation, and at the end you want to say, well, what was my error on this version of the model? Okay, well, that error value is somewhat privacy preserving. It just tells you over all the inputs to the model what's the total error that it's now predicting, and it also tells you whether I should continue to keep training or not. That would be a great value for a data grant to release to the local server, so they could know, oh, I need to keep doing. Now, if they want to like instead see like how some property or data, that's a different computation. They're not going to be able to decrypt that value because it's not going to match the computation to figure out what is the current error rate. So in essence, it is a mechanism to disclose where both the data owner and the data user are agreeing on a particular function where the result can be seen. So we have this value that was computed by the data user. We have this data grant, which is encrypted under the same key as the data itself that comes from the data owner. And then if this value was computed by that G of X that is associated with this data flow signature, these two will match. And then you can decrypt that one value, just that one value. And that's a really powerful mechanism. If you compute any other computation, you will absolutely get a different data flow signature. Finding another computation that produces the same data flow signature, that's called a pre-image attack on a cryptographic hash. And that is what Bitcoin mining is times a million. So that's a really, really difficult task. So you're not going to be able to do that, essentially. So really powerful mechanism, super simple, super simple. The way programmers interface to TrustForge is they just get encrypted variables. So our C++ library, instead of uint32 and uint64 and int32 and int64, you get TF, TrustForge int32, TrustForge int64. And these are just encrypted versions of the variables. Typically, a variable is about 2 to 4 times as large encrypted. They're either 128, 192, or 256 bits, depending on how big the underlying data type is. And this works for integers, floating point, IEEE floating point, booleans, strings. They're all supported in there. And so programmers just essentially take their original program and then they privatize information that they want to receive from a third party and they themselves don't want to see, or information they want to make sure an attacker that's looking at the system cannot ever know. And then if there's any results produced by computation from an encrypted value, that result always has to be encrypted. There's no way around that. And if there's any exceptions, those are encapsulated in there as well. Now, one of the challenges with programming in TrustForge is if you want to make a decision on a secret, you can't have an if statement because you can't see the secret. So the way we resolve that is you have to do essentially predication. You have to take the encrypted secret and you have to use this CMove primitive that the Enclave provides, where if this is true, this value is passed to X, and if this is false, this value is passed to X. So, and then I can apply any computation I want to the secret to get, if it's not secret, I'm gonna move Y, otherwise I'm gonna move X. So. And then mind you, because we use this randomized ciphertext, you can't look and see if X is the same ciphertext as this, because every time you do a computation, you're going to get a totally new version of ciphertext. So there's no analyzing the output of these operations to figure out if secret was true or false. Really powerful mechanism. And then if you want to index memory with a secret, you have to use what's called an ORAM primitive, where essentially the RAM is scanned, and then we snatch out the value you want based on the secret index. You have to touch every location of memory, and that's really expensive. In fact, these operations are when the performance of the program can become very inefficient. And I always tell my students, and we always say this at the startup as well, is that using an ORAM primitive is like drinking in the morning. It is a warning sign that you need to redesign your algorithm. Now, one thing we found is that the best way to deal with ORAM primitives, use them when you first convert your algorithm, but then get rid of them by redesigning your algorithm. In every single situation, we've been able to get rid of them. And then you essentially bring your algorithm back to the same time complexity as it was in the decrypted form, now running in the same time complexity in the encrypted form, which is valuable for performance. Just to give you an example of what it looks like when you convert a program, this is a Newton-Raphson solver on TrustForge. This is using Newton's algorithm to sort of hone in on a transcendental result. It's doing, for example, like a square root. And, initially the algorithm isn't converged. Now, if you're familiar with this algorithm, typically it'll exit this loop when the max error is more than the current error. And so we can't exit that loop early, so we're always going to do the maximum number of iterations. So you can't have a loop exit based on a secret. And how is that enforced? It's enforced because you can't see the current error value. You can only generate a Boolean that's encrypted with the current max error. And so based on that encrypted value, we either take the Newton step in new guess, or we take the old value. Now, can the programmer know if they took the new guess or the old guess based on the fact that it's convergent? They don't know, because these values are all encrypted. So it's pretty easy to write this what's called data oblivious style code because you can't see these secrets. It's naturally enforced. And then when you're done, you return the value. That'll have your transcendental in it. By the way, it would be a PhD thesis to write this particular algorithm on homomorphic encryption because this operator is nonlinear, so you probably have to do a Taylor series expansion to implement that. There's no divide on homomorphic encryption. That's a nonlinear op, so you're going to have to come up with some kind of maybe logarithmic solution here. And this is going to be, CMove is going to be really hard to implement as well. So one of the advantages of the hardware world for encrypted computation is just super easy to program from the get-go, really easy. So let's just sort of recap what are the capabilities you get in this TrustForge Enclave. So you get data encryption, ultra high performance or ultra high strength data encryption. It's authenticated. It's high entropy. You get encrypted, any computation you want to do on that encrypted data you can do using, and it's floating point, booleans, integers, all the basic RISC ops. Can't branch on the data, you can't index memory with the data, but you can certainly get around that with data oblivious programming techniques. And then every piece of information that's computed carries a proof as to how it was, concise data flow hash that describes how that value was computed. And then using those verified computations, you can implement safe disclosures with a data flow grant. Now, earlier I talked about how we have the world of advanced cryptography and we have the world of trusted hardware, which is TrustForge Enclave. In the world of like traditional encryption, all you can do is data encryption, right? So if you've ever used any end-to-end encryption like Signal app or WhatsApp, that is the form of privacy that you can get with data encryption. There's no computation on the encrypted value. There's no verification of what's inside that encrypted, and there's no way to disclose information, which is good. It's good for messaging. With homomorphic encryption, you can add this encrypted computation capability, but you can't verify what it was done. When I ask a homomorphic encryption server to do a computation for me, I have to trust that that server did the computation that I asked for. If I want to actually go to verified computation, I need to use another technology called ZK proofs, zero knowledge proofs, to prove that the integrity of that computation was intact by essentially evaluating assertions over how the value was computed. So while it's not the same as what we're doing with data flow hashes, you can essentially get to the same place with ZK proofs in the advanced cryptography world. But there's really nothing that allows safe disclosure in the advanced cryptography world. And I'll often pose the question to people in the advanced cryptography world, how do you implement useful privacy programming capabilities if you can't ever let the server release a value to see it? And usually the solutions they come up with is they need to have a third-party server that that's trustworthy to release that value, which then introduces all the hacking back into the threat model that you really don't want there. So they don't have a solution in this space. They have theorized that it's something called functional encryption, but they don't really have anything implemented in that part of the world yet. So by leaning into trusted hardware, we can actually sort of zoom ahead of homomorphic encryption and zero knowledge proofs and really start building systems that have this capability. One day, homomorphic encryption and zero knowledge proofs will, build this notion of functional encryption, and they too will be able to do this as well. But they can't do that today, and they certainly can't do encrypted computation and verified computation at the level of performance that I can. So now, one of the things we've done is we did a startup out of University of Michigan called Ajeta Labs, and Ajeta has deployed a TrustForge Enclave into Amazon AWS and Microsoft Azure. The way we deploy it is with FPGAs, so we can put this hardware enclave into the cloud. It's 6% of an UltraScale plus FPGA, which is a reasonably old FPGA. It's about 190,000 gates. It's super tiny. The implementation we deploy is logic locked, so unless it communicates home with a server, it can't bring this hardware up. It's watermarked, so we know whether or not it's our design that's in the FPGA, and it supports something called forward secrecy, in that if a judge, for example, were to tell us, put a backdoor in this enclave so we can see this data, that new enclave that we made would not be able to open the data that the old enclave could, because we don't know what the secret key is when we build a bit stream for these. We generate it locally and then we delete it. And it's really simple. 190,000 gates. It took two person years to build fuzz and formally verify this design. And then in the marketplace, it does compete with fully homomorphic encryption. That is the space that we competed, and multi-party computation. And just to give you a sense of the relative performance of these, this right here, that 55x is TrustForge Azure. That is, we get about a 55 times slowdown pushing computation to an FPGA through a PCIe bus connection. So almost all that latency is not encryption. It's PCIe bus and FPGA speed. But even going to that board for that FPGA, we're a couple order of magnitude fast, at least an order and a half magnitude faster than Seal homomorphic HE. This is Microsoft's HE product, and it is levelized, not fully homomorphic HE, and it is hard to program, right? So it doesn't have any of the capabilities that more capable FHE has. It's built for speed, and it's 880 times slower on the same benchmarks. Now we work with Intel and we have access to their integrated FPGAs. When we put this on their next gen integrated FPGAs, we're only about 18 times slower. And we've also looked at partnering to put this into an SoC where we could make the entire Enclave an ASIC. And we estimate we would be within about 5x of native execution, which is still slower than Intel SGX, which is probably less than 3x slowed down for software running in it. But the advantage we have over Intel SGX is there's no software in the box to hack, and it's cryptographic strength. Security without any digital side channels. If you're aware of Intel SGX, there's software in there that people hacking that software is really a sport in the security community today, and it's loaded with digital side channels. So the security profile of this solution is way better than this solution at only a slightly higher performance. If you want to get to the advanced cryptography techniques that are more programmable, you got to look at something like multi-party computation, which we're many orders of magnitude faster than that technology and need a lot less hardware. This is distributed systems to implement this. And then if you look at like integer fully homomorphic encryption, so you can do arbitrary deep linear computation, we're again 5 to 6 orders of magnitude faster than that. And then really the holy grail of FHE is what's called Boolean FHE, where instead of actually implementing integer computations, you're implementing NAND gates. In that world, you can build anything you want, and you can have a easily programmable, fully homomorphic system. A great example of this is Zama's concrete framework, which it just takes Python code that's data oblivious and converts it to fully homomorphic computation. Beautiful, absolutely beautiful. And then it's programmable like TrustForge. It's 100 million times slower than TrustForge. So it's a big difference, but it's more secure. It's more secure. This doesn't have those analog side channels. One of my PhD students who recently graduated, she's now Lauren Biernacki. She's now a professor at Lafayette College. And in her thesis, she took this Enclave and she packaged it up as a functional unit and put it into a microarchitecture. And then she did a little bit of caching of decryption and then proved that there were no side channels, that all of the indexes to those caches was information already known by the attacker. So there was no new information leaking out of those caches. And she got within 17% of native performance. And in fact, the bulk of the slowdown was not in the crypto. The bulk of the slowdown was in the changes to make the program data oblivious. And then I've got another paper I did with Lauren that says we can address a lot of those problems by just getting better algorithms. So I envision a day when hardware secure computation can be only a few percent slower than native computation. Really, really basically almost as fast. And that's a really exciting place to be. Now, that computation will never subsume the value of fully homomorphic Boolean computation, because that computation has a better security profile. It doesn't have to suffer from the analog side channels. In the meantime, I'm going to work on the analog side channels and make it harder and harder to measure information in these hardware enclaves. But ultimately, there'll always be a space for trusted hardware and advanced cryptography. Where that breakpoint lies on where does the security become important enough to me that I move over to the FHE side rather than the trusted hardware side, that'll really be a function of how well we can accelerate FHE, which is very important, and how well we can eliminate analog side channels in the trusted hardware. So it's a really exciting space to be in at the juncture of advanced cryptography and trusted hardware. When you go into commercial deployment, people always want you to red team your hardware, which is where you essentially hire a team of attackers, white hat attackers, to penetrate your hardware. And we did this with one of our companies we've been working with called Incutel. And Incutel is kind of the VC arm of the 3-letter secret agencies in the United States. And we red teamed with Incutel and Blue Bastion, which was the actual red team, for 3 months. And it was a really cool experience. We met with a team every week, and basically, they would give us ideas on where they were going, and we would give them recommendations, and they essentially had access to all of our IP, even the design IP. And they found no vulnerabilities in the threat model. In fact, after the 3 months that we were red teaming, our threat model didn't include analog attacks. So after a little bit more than 2 months, they said, we're not going to find anything here. Let's switch over to the analog attacks. And then they did analog attacks, which was really useful because we got to learn, how we might be attacked on the analog front. But they still couldn't find anything on that front because our circuits were just so tiny. They couldn't see enough signal at that point. So that was really exciting. And they did all of what we call the stupid FPGA tricks. Like they would load our Enclave into an FPGA, and then they would reload the FPGA with something to scrape all of the logic and VRAM values out. So it was a really interesting activity to work with Blue Bastion. I was super impressed by their abilities. They found no vulnerabilities, and they themselves had never encountered such a thing, ever. It was fun. In fact, I'll say when we worked with a team, the first day we met with them, we told them this has 0 software trust and no side channels and encapsulates exceptions. They looked like at us like we were a bunch of idiots. Like we're gonna show you how many side channels and vulnerabilities you have. And then after 3 months, they were just in awe. They were in awe of this piece of hardware. So it was a really exciting activity. But I always like to remind people, what's the value of a red team effort where you find no vulnerabilities? And I would say the value of that is essentially 0, right? You don't know that there's no vulnerabilities in this. And that's why I'm really proud of the work we did with Princeton, with Sherrod Malik and his students at Princeton, where we did formal verification of the TrustForge Enclave, which was really a 2-layer process where we use proof assistance to describe the semantics of the instructions that the Enclave implemented. And then those proof assistants would then compose arbitrary sequences of those instructions. So given that we can do any combination of those instructions, there are no side channels, direct disclosures, analyzable ciphertext, etc. There was a bunch of vulnerabilities we analyzed. As long as the underlying RTL meets these requirements, and these are what we called hardware proof requirements. Like every ciphertext that's produced has at least 64 bits of entropy in it, and there's no backdoor in the hardware to release a value, et cetera, et cetera, et cetera. And then we used a tool called Jasper Gold to analyze the underlying RTL of the design to show that it didn't violate those proof obligations. That ends up being an end-to-end proof that you cannot write a program which can direct or indirect disclose with a digital side channel. And that was published in ACM CCS, and that won a Distinguished Paper Award at ACM CCS. Super proud of that work. And so anyway, that's where we are today. We have a product based on this. We have a great line of research based on this. I'm today focusing a lot on programming these systems and how to ease the burden of programming, even though they're way easier to program than advanced cryptography techniques. I still want to make it even easier. So we're working on like tools to help with that. But then I'm also really focused on analog side channels and hardware Trojans. How do we get rid of all those to really close the gap between advanced cryptography and trusted hardware? But in the last decade I've been working on this, I've learned so much about how to build secure systems. And I just kind of want to encapsulate that into a couple of, I would call these Todd's axioms for hardware design, secure hardware design. And the number one axiom, if you get anything out of this talk, is don't ever trust software, right? If part of your security for confidentiality, integrity, availability lies in software, then you are not cryptographic strength. You will be let down by the software. So we need software. Software is the function that our systems implement. It's the flexibility and the programmability of the system. We love software. We just don't trust software. It's like that friend you have where you love hanging out with them, but you never ever expect that they're going to show up to this party, right? Because you don't trust them. You just enjoy being around them. That's what software is, right? It's important, but it is not trusted. And then we will never stop microarchitecture side channels. There's no way. If you're building for performance, there will be side channels. Don't even attempt to stop those side channels. Instead, move your trusted entity off into its own part and design that for security. You really need the fast part and the secure part. I always like to tell companies that get beaten up for Spectre and Rowhammer and all this other stuff, like, why don't you build something off to the side that's more secure, like TrustForge? And then when someone comes and said, look at this information I leaked out of your main system, instead of saying, oh, I'm so sorry that there's a side channel in our microarchitecture because we'll never get rid of our side channels, you say, hey, why aren't you running that software on this other thing where we prove there are no digital side channels? You know, that to me seems like a much better approach. And if you could provide privacy enhanced capabilities with that component, it's no longer a tax. It's value added to the system. Now you're providing a value to your customer and better security at the same time. So, you know, I love the idea of minimizing trust in hardware, verifying that it doesn't have those digital side channels. And we stop those channels essentially by formally verifying that hardware and then isolating it from the main system. And then finally, anything that moves outside of that box, you've got to protect with cryptography, because cryptography is the only superpower in security. It's the only thing that you'll be able to rely on. I always say, like what part of your design will force you to cancel your wedding, right? The cryptography will never force you to cancel your wedding, right? Because cryptography ages as computing progresses along Moore's law. Like, oh, when you think about vulnerabilities in cryptography, it's like we should move from 1,000-bit keys to 2,000-bit keys within the next 10 years. Or we should move from RSA to post-quantum algorithms before 2025. Some of the quantum people might be a little bit upset about that number, but you know, soon, in a few years. Whereas if you're dealing with any kind of software issues, and part of your security system is software, it's like you can get a 0 day at any time of the day and you got to cancel your next week. It's a bad thing to be in. So cryptography is the superpower, and the more we use it, the better the outcomes we'll have. And I hope I really, you know, taught you that, like, trusted hardware is really a viable approach to advance privacy and security in the system. And that's why and it's not software, you know, it's either advanced cryptography or it's trusted hardware. That's really the solutions we got to look to. And so that's why I think advanced hardware is going to move way faster than advanced cryptography. It's going to deliver more quickly, be more programmable than those other solutions. Those other solutions are always more important because they have a better ultimate security profile. But as hardware security architects, we can punch ahead fast and we can deliver for privacy. And privacy will allow you to add value to the system, and it'll allow you to get these technologies into next generation hardware systems. We've got it already in the cloud. People love the technology. It's really quite capable. So what an opportune moment it is to be a hardware security architect. We get to push the ball forward on security. We get to push the ball forward on privacy. And, you know, really, it's not really the ability that anybody in the world of software could do. We get to do that. That's super exciting. Work with our brothers and sisters over in advanced cryptography. Pull the best ideas that they have into our hardware world. provide more performance, more programmability today so that we can implement the applications and the capabilities today that they over in the advanced cryptography world cannot. And then as we can accelerate their technologies, as they can make their technologies more efficient, we can move more of that high security into the trusted hardware side. Super exciting. And I'm delighted to be a part of this community. So if you're not a hardware security architect, think about becoming one. If you want to learn more, well, you can take my hardware security tutorial on YouTube, almost 8 hours of content that'll teach you more about that. If you want to learn more about TrustForge, you can check out our IEEE paper. The underlying technology we call sequestered encryption. We sequester keys and data into the hardware. And then you can learn more about our verification in the CCS paper. You can learn more about the implementation in the startup in these 2 patents. And then you can go check out Ajeta Labs if you want to see the startup's capability as well. Thank you so much for your time. I'd be delighted for your feedback on this talk. So if you want to leave me any feedback, if you got any questions, just leave a comment on this video or hit me up on my LinkedIn, and I'm glad to chat anytime. Thanks so much. Take care.